Hopefully you guys can hear me right now. I've started the stream. I am just closing this window from here and I will be just running or doing things from this Docker. Docker images start with the base layer. Every time you add new content, watch the time. Docker add new layer. Consider the following oversimplified example of building a simple Python application. Your corporate policy mandates all application be built on top of official Ubuntu 2.24 image. This means that official 24 Ubuntu image will be the base layer for this app. Installing Python will add second layer. Your application source code will add third layer. The final image will have three layers as shown as figure 6.8. Remember, this is an oversimplified example for demonstration purposes. It's important to understand that an image is the combination of all layers tagged in order they were built. Figure 6.9 shows an image with two layers. Each layer has three files, meaning the image has six files. Meaning the image has six files. It also shows that the layers are stored as independent object and the image is just metadata applying identifying the required layers and explaining how to stack them. Cool. In this slightly more complex example of three layer image in figure 6.10, the overall image only presents six files in the unified view. This is because file 7 in the top layer is the updated version of file 5. Directly below this situation, the file layer obscures the file directly below it. This means that you can update the file and the image by adding new layers. Okay, got it. Under the hood, Docker uses storage drivers to stack layers and present them as unified file system and image. Almost all the Docker steps use overlay 2 driver, but ZFS, BTRFS, VFS are alternative options. However, whichever storage driver you use, the developer and user experience are always the same. Figure 6.11 shows how the three-layer image from figure 6.10 will appear on the system. All three layers tagged and merged into single unified view. Sharing image layers. As previously mentioned, images can share layers, leading to efficiencies in space and performance. One of the earlier Docker pull commands generated an already exist. One of the earlier Docker pull commands generated an already exist message for one of the layers it pulled. This occurred because one of many Docker desktop extensions had already pulled an image that used same layer. As a result, Docker skipped that layer as it already had a local copy. Here are the code from earlier. Shows two images sharing the same layer. Red is Docker pull, red is latest pulling. Download okay, already exist this line. Local repository independent layers. Image is being used. Image is being used. Layers are also shared on the registry side. This means that you can store a lot of similar images in a registry, and the registry will save space by never storing them more than a single copy of any layer. But they might do because of backup and redundancy. They might do it backend. Pulling images from digest. So far you have seen how to pull and work with images using names, tags. While this is the most common method, it has a problem. Tags are mutable. This means it is possible to tag an image incorrectly and give a new image the same tag as the older one. An extremely common example is the latest tag. For example, pulling Alpine latest tag a year ago will not pull the same image as pulling the same tag today. Consider a quick example outlining one potential application of trusting mutable tags. Imagine you have image called golf track colon 1.5 and you get a warning that it has a critical vulnerability. You built a new image containing the fix and push the new image to the same repository with same tag. Take a moment to consider what just happened and the implications. You have an image called golf track 1.5 that's being used a lot of containers in your production environment, and it has a critical bug. You create a new version containing the fix, so far so good, but then you make a mistake. You push the new image to the same repository with the same tag as the vulnerable image. This overrides the original image and leaves you without a great way of knowing which your production containers are using the vulnerable image and which are using the fixed image. Both images have the same tag. This is where image digest come to the rescue. Docker uses a content addressable storage model where every image gets a cryptographic content hash that usually called the digest. As these are hashes of an image content, it includes two different images to have the same digest. It's impossible for two different images to have same digest. It is also impossible to change an image without creating a new unique digest. Unfortunately, Docker lets you work with image digest instead of names. If you already pulled an image by name, you can see the digest by running a docker images command with digest flag. Docker images digests alpine SHA. Yeah, these are different images. Yeah, here. If you want to find image digest before pulling it, you can use docker buildx image tool command. The following example retrieves the image digest for docker pull nickel Paulton Kubernetes book @. It is also possible to directly query the registry API for image data, including the digest. The following curl command queries the Docker Hub for digest of the same image. Curl https image hashes and layer hashes. You already know that images are just a loose collection of independent layers. This means an image is just a manifest file with some metadata and a list of layers. The actual application and all its dependencies live in the layers. However, layers are fully independent and have no concept of being part of an image. With this in mind, images and layers have their own digests as follows. Image digest are a crypto hash for independent manifest files. Layer digest are the crypto hash for layers content. Images have layers have crypto hash, images also have crypto hash. This means that all changes to layers or images manifest result in new hashes, giving us an easy and reliable way to know if changes have been made. Content hash, distribution hash. Docker compares hashes before and after every push and pull to ensure no tampering has occurred. However, if it also compresses it also compresses image during push and pull operations to save network bandwidth and storage space on the registry. As a result of this compression, before and after hashes won't match. To get around this, each layer has two hashes: content hash, distribution hash. Every time Docker pushes or pulls a layer from registry, it includes the layer distribution hash and it uses this to verify that no tampering has occurred. This is one of the reasons why hashes in different CLI and registry outputs do not always match. Sometimes you're looking at the content hash, other times you're looking at the distribution hash. This is actually important. Multi-architecture images. One of the best things about Docker is its simplicity. However, as technologies grows, they inevitably get more complex. This happened for Docker when it started supporting different platforms and architectures such as Windows, Linux, and variations of ARM, x64, PowerPC, S390X, and more. Suddenly, there were multiple versions of same images for all different architectures. Developers and users had to put in significant extra work to get the right version. This broke the smooth Docker experience. Multi-architecture images to rescue. Fortunately, Docker and registry API and that adapted and became clever enough to hide images for multiple behind a simple tag. This means that you can do a Docker pull Alpine on any architecture and get corrected version for the image. For example, if you are on AMD 64 machine, you will get AMD 64 image. To make this happen, registry API supports two different constructs: manifest list. Oh, now this is actually working. Earlier it was not. List is exactly what it sounds like, a list of architecture supported by the image layer. Each supported architecture then has its own manifest list that layers use to build. Docker build X image tool inspect Alpine. Default tag latest. Okay. Already exists. See, then it is using some already exist latest soccer Docker build image tools inspect Alpine the fuck manifest is for altogether a different architecture. If you look closely, you'll see manifest 5.26 application vnt docker dot distribution manifest list is the manifest list. Each media type refers to the manifest of specific architecture. Shows how manifest list and manifests are related. On the left, you can see the manifest list for entries on different architectures supported by the image. The arrows show that each entry in the manifest list point to the manifest defining the. Let's take a quick example. Assume that you're using Docker desktop on an M3 Mac where Docker runs inside a Linux ARM VM. You ask Docker to pull an image. Docker makes the relevant calls to the registry API to request the appropriate manifest files. Assuming it exists, Docker then parses it to a Linux ARM entry. If Linux ARM entry exists, Docker retrieves its manifest, parses it for the crypto ID of its layers, pulls each individual layers, reassembles them into an image. Let's see it in action. The following examples are from Docker Desktop on ARM-based Mac and Docker Desktop on the AMD-based Windows machine running in Windows Container Mode. Both start a new container based on official Golang image and execute Go version command. The output shows that version of Go and host platform and CPU architecture. Notice that how both commands are exactly same and Docker takes care of pulling the correct image. Both images are large and may take while to download. You do not need to complete these commands yourself. The next one, ARM64 example, Golang Go version. Run Golang Go version. If you already seen how these Docker buildings understood command to see the manifest list and the manifest for the image, you can get similar information for Docker manifest command. The following example inspects the manifest list for the official Golang image. So you can see it has images for Linux and Windows on variety of CPU architectures. You can run the same command without the grep filter to see the full JSON manifest list. Windows users should replace the grep command with select string architecture OS. Okay, let me do it myself. Clear. Docker manifests. Manifest inspect alpine grep architecture backslash OS. Let it run. Manifest inspect alpine grep architecture alpine OS. What is happening? Why is it taking so much time? AMD64 ARM64 386 PP 64 LE RISC-V 64 S390X. What is this 390X? I know RISC-V is S390X. IBM. These are discontinued mainframe 5th generation, introduced in 1990. Videos are there. Living fossil introduction to pulling the right image for your system is one thing, but what about building images for different architectures? Docker buildx command makes it easy to create multi-architecture images. For example, you can use Docker Desktop on Linux ARM to build images for Docker, build images for Linux AMD, and possibly other architectures. We'll perform builds like these in future chapters, but Docker buildx offer two ways to create multi-architecture images: emulation, build cloud. Emulation mode performs builds for different architecture on local machine by running a build inside a QEMU virtual machine emulating the target architecture. It works most of the time, but it is slow and doesn't have a shared cache. Build Cloud is a new service from Docker that performs builds in cloud on native hardware without requiring emulation. It is very fast and let you share common build cache with teammates, and is seamlessly integrated into Docker Desktop and any version of Docker engine using version of buildx supporting the cloud driver. It also integrates with GitHub Action and other CI solutions like Jenkins. At the time of writing, Docker Build Cloud is a subscription service you have to pay for. We'll use both in future chapters, but I ran the following command to build AMD and ARM version of TU demo using Docker Build Cloud. Cloud पे चल रहा है ये तो. Vulnerability scanning by Docker Scout. Lots of tools plugin exist that scans images for known vulnerabilities. We'll know Docker Scout as it is built into almost every level of Docker, including Docker CI, Docker Desktop, Docker Hub, and scout.docker.com. It is a very sleek service, but it requires a paid subscription. Other similar products and services exist, but most require paid subscriptions. Recent version of Docker Desktop have Docker Scout CLI plugin pre-installed and ready to go. If you're running a different version of Docker, you may install CLI plugin from GitHub repo. You can use Docker Scout to get quick vulnerability overview of the image. Okay, it is paid. Then let it be paid. How to install it? I will install it right now. It requires a lot of things to be done. What should we do? Copy the binary to the scout directory .docker. Make it executable on Mac. Copy the scout directory. Nv docker scout nv ls-l. Yeah, so nv scout to docker cd docker cloud ls chmod, we are making it executable, docker scout, authorized binary, add scout directory to your dot. pwd. So this is our less config.json, then config.json, full path slash root slash docker scout. I think that would be enough. That would be enough. That would be enough. That should be enough. Script installation. GitLab circle CI. Wait it. Scout. Will it work? No, it won't work. If you don't have Docker ID, head over to Hub. You can log in with personal access token, running Docker login. Yeah, it is a paid tool. We cannot do it. List vulnerability. CVE. Cool. Portal provides overview. Dashboard allows you to configure policies and lets you. So this is somewhat like SonarQube. You can delete images by Docker RMI. RMI is short form for remove images. CD Docker images, Docker RMI. Find latest RM. What if I write star? Alpine latest busy GHCR, then Nginx, then Nickel Bolton Kubernetes, then Nickel Bolton TU, then Node, then Redis, then Ubuntu. Everything deleted. Docker images. Oh, we still have Mongo. Mongo I did not configure. Docker RMI Mongo 7. Docker PS. Nothing is there. You can one by name, one by short ID. Even name used by the container or referenced by one or more tag. or you can force this operation by f flag, but you should do this forcing docker to delete and use by a container will untag the image and leave it on system as dangling image. A handy way to delete all images is to pass a list of local images ID to Docker RMI to pass a list of local. You should use this command with caution. If you are doing along Windows, it will work only in PowerShell terminal. Docker pull Alpine Fedora Ubuntu Node.js Alpine Fedora is done. Fedora Ubuntu Debian running layer Debian. Now we will pull Go will be huge. Python is also there. Python is a big one. Extracting pull complete. Docker RMI. Wait. Docker images -q. Config file invalid character .docker. Looking win root .docker config.json file. I think we shall remove it. Let's see. Character.docker config.json. Sorry. I scout. Okay. Who cares about it? I can always delete Docker and install new Docker. Who cares about it? So Docker RMI, so this can be an argument for this new command Docker RMI and Docker images -q is only for the what is this list of image IDs -f flag. Huh? The fuck happened? -f flag. Docker Okay, I used hyphen. I used hyphen and hyphen f. Hyphen f. Now it will work. Docker images. Now it is not there. Images. The command docker pull is a command to download Docker images to list the images in Docker host local repository images caching. Docker inspect gives you wealth of images related metadata in nicely formatted view. Manifest inspect lets you inspect the manifest list of the image stored in the registry. The following command will show the manifest list for the regctl image. Docker buildx is a CLI plugin that works with Docker latest building in Docker Scout to perform image. It scans image. Is Docker Scout paid? Is Docker Scout paid? Both free. It isn't an no cost under Docker. 3 remote repositories. Okay. But important theory and fundamentals of image. You learned that image contain everything you needed to run an application as a container. You can start one or more container from a single image. Under the hood, Docker constructs image by stacking one or more read-only layers, presenting them as unified object. Every image has a manifest that lists the layer that make up an image and how to stack them. You learn image names are also called tags. They are mutable and they don't always pull the same image. For example, pulling alpine today will not put the same image it will a year from now. Fortunately, every image gets an immutable digest that you can use to guarantee you always pull the same image. Docker have a notion of curated official images that could be safer to use than unofficial images. However, you should always exercise the caution when downloading software from internet. Every official images, even official images from Docker Hub. Images share layers for efficiency. Docker makes it easy to build and pull images for a lot of different CPU architectures such as ARM and AMD. Docker Scout scans images for known vulnerabilities and provides remediation recommendations to require Docker subscription, and it integrates into Docker CLI. Tour of containers, the runtime sibling of images. Cool enough, cool enough, cool enough. Now I will rest and then we will come back again. Working with containers. We'll do this later. Now I will study C language. Exit, exit, labctl playground list. Okay. Labctl playground stop. Because this is a persistent playground, so that is why it is taking a lot of time to stop, because it is a persistent playground. So I will stop streaming.